Good day, ladies and gentlemen. It is my pleasure to give a presentation about wearable magnetic sensors and skins. My name is Jürgen Kosel. I'm the head of the research unit Sensor Applications at Silicon Austria Labs, and I'm adjunct professor of electrical engineering at the King Abdullah University of Science and Technology. In this presentation, I will first start with an introduction in which I will give an overview of the different magnetic sensing technologies and also some history. Then I will dive deeper into specific sensors, which is the Hall effect sensor, the giant and tunnel magnetoresistance sensors, the giant magnetoimpedance sensors, and then eventually I will talk about magnetic skins. So let's go ahead with. First of all, magnetic sensors convert magnetic signals into electric signals. Thereby, they operate in a conductless mode, which is one of the most important advantages that make them so prominent in many applications. Another thing is that typically we're not interested in the magnetic field as such, but we are interested in something else, like a direction, the presence of an object, a rotation, a current, an angle, and we use the magnetic sensor to indirectly measure those parameters. The first magnetic technology that we are aware of was the so-called south pointer, which was used around 400 BC. It is an iron oxide shaped in the form of a spoon and placed on top of a copper plate, and it was used by fortune tellers to tell people's future directions and guide them in their way of life. It took about 1500 years before this technology was used for navigational purposes. In a Chinese war book from 1044 AD, we find the description of the so-called south pointing fish, which was actually a magnetic compass. The fish was made again of iron oxide, and it was floating on water in a bowl. And nowadays magnetic sensors are used in many different applications. We use them for speed or angle sensing, as position sensors, as compasses in many of our smart tools and instruments. Of course, in magnetic reading heads, and there the technology progress of the magnetic sensor technology is particularly prominent, and also for magnetic resonance imaging and many others. But there are also a lot of new upcoming applications where we see magnetic sensors playing a big role. For instance, renewable energy, where photovoltaic power plants require maximum power point tracking, which in turn requires electric current sensing. Early cancer detection is a rather new area for magnetic particles, and specifically magnetic nanoparticles, which by now are also studied for the destruction of cancer. And then we can use them for construction monitoring to monitor the corrosion of reinforcements in bridges or buildings, as well as we use them nowadays for magnetic random access memories. And I think we will see a lot of other new applications where magnetic sensor technology will excel. So then let's get into the Hall effect sensors. The Hall effect is actually a very old effect. It was discovered in 1879 by Edwin Herbert Hall during his doctoral thesis at the Johns Hopkins University. He noticed a small voltage across a current carrying wire when a magnetic field was applied. And this was the Hall effect. This sensor is extremely practical and easy to fabricate, and therefore has found many applications. For instance, here we see an old version of an iPhone and an arrangement of Hall effect sensors inside of it. The Hall effect itself is strongly linked to the Lorentz force. And the Lorentz force is a force on a charge carrier that is moving in a magnetic field. So let's take, for instance, this metal strip that is conducting a current. The current flows as indicated here by these arrows, meaning the electrons will flow in the opposite direction. And we apply now a magnetic field that points from the bottom up, indicated here with H, and this will cause the electrons to divert to the left side in this case, and the left face of the current carrying wire. We end up with positive charges on the right face, and therefore we have a Hall voltage across the wire. And this Hall voltage can actually be derived very easily from the Hall field. And what we find is that the Hall voltage has some very attractive and interesting features. One of them being that it is directly proportional to the magnetic field, which means we have a linear sensor. The other one is it's proportional to the current. Hence, the more current you apply, the more sensitivity you will get, or the more signal you will get. It is inversely proportional to the thickness, and therefore thin layers are advantageous. And this is why, for instance, the MOSFET as a simple structure is often used as a Hall effect sensor. And this is also has also the benefit of the simple and well-established fabrication. And then we have here the Hall constant, which is simply 1 over the number of carriers per unit volume, or the carrier density, and the charge itself. And this Hall constant is quite useful because from the Hall constant we can determine the density of carriers in our material, and this is therefore a nice method in the semiconductor industry. Also, if we divide the Hall constant by the resistivity, we actually get the mobility of the carriers. Note also that because the Hall voltage is inversely proportional to the carrier density, semiconductors have a higher sensitivity than conductors. For instance, silicon has around 10,000 times higher sensitivity values than gold. And finally, from the orientation of the Hall field or Hall voltage, we can also determine the carrier type, whether it's a P or N type carrier. I would like to introduce you to a Hall effect sensor that is fabricated with a rather recent technology which is called laser-induced graphene, or also often called laser-scribed graphene. This is a method that allows you to scribe graphene on substrates with the laser, similar to a printing process. It's a method that works in the regular environment and does not require any fancy or expensive instruments or substrates. You can fabricate traces of graphene which are conducting and also of course piezo resistive and have a lot of other features in a simple one-step fabrication process. Here you see an array of interdigitated electrodes that are fabricated in this way, and you see here a demonstration of the flexibility of such sensors. Here we see a typical example of a large array of Hall effect sensors on a flexible substrate. In this case the sensors are basic Hall bars, as you can see here, but obviously you can generate any kind of Hall effect sensor with this method. This electron microscope image shows a cross-section of a processed polyimide, which was originally around 150 micrometer thick, and we can see here a roughly 30 micrometer thick layer of laser-induced graphene. Very clearly also we can see here the poro structure. Another important result is this thermal gravimetric analysis of the laser-induced graphene, which shows that there is almost no loss of mass up to a temperature of around 500 degrees Celsius, which makes this material very suitable for high temperature applications. Further, here we see the Raman spectrum of the typical Raman spectrum of laser-induced graphene, the D peak, which is associated with defects, the G peak, which indicates some graphite structures, and the 2D peak. The pronunciation of this usually is used as an indicator for the quality of the laser-induced graphene. The characterization of a Hall effect sensor is straightforward. You apply a current along your Hall bar and you measure the Hall voltage transversely to the current direction. Then you apply a magnetic field perpendicular to your structure and you end up with a Hall voltage as a function of the magnetic field. This should be a linear dependence, and this is indeed what we find here. From -7 to +7 Tesla at 100 microampere current, we find a linear response with a sensitivity of 1.12 volts per ampere Tesla. And these sensors can be used for many different applications because they're flexible, they are temperature resistant and durable. So we use them, for instance, here in a tactile sensor. This tactile sensor is composed of 3 layers. The bottom layer is the laser-scribed graphene Hall effect sensor. The top layer is a magnetic skin, which I will talk about more in detail later, but basically it's a flexible permanent magnet. And the middle layer is an Ecoflex layer, which is a very soft and flexible separation layer. And as we apply a force from the top, we squeeze the structure and we bring the magnetic skin closer to the Hall effect sensor, and this results in an increase of the Hall voltage, and we find a linear response of the Hall voltage to the applied force. Here we see a couple more characterizations of the laser-induced graphene Hall effect sensor, and it reveals some interesting findings. First of all, if we bend the laser-induced graphene sensor, we actually reduce the effective area from which we capture magnetic flux, and therefore the sensitivity decreases as we reduce the bending radius. We tested the sensor over bending cycles, up to 1000 cycles, and we used 3 different sensors for this, and as we can see, the sensitivity did not change with the bending cycle, so it's actually quite robust. Then, of course, as I told you, and I've shown you before, laser-induced graphene is very temperature resistant. So we tested it here with respect to the Hall sensitivity, and up to a temperature of 400 degrees there is actually no change. And this is a particularly attractive result, as this sensor is a flexible sensor which can be used for harsh environments in high temperature. The noise characterization is shown here. We found a corner frequency where the 1/f noise crosses over to the thermal noise of around 20 Hz and a thermal noise floor of 54 picovolts per square root of Hertz. Now, it's not only attractive for a Hall effect sensor, but laser-induced graphene can be utilized for many different sensors. Here, for instance, you see a salinity sensor, which is a 4-probe conductivity cell, which we used and tested in the Red Sea. And the flow sensor is set up here, a drag flow sensor, and then you see a pressure sensor and a temperature sensor here. Pressure was tested up to, in this case, 12 megapascal. Eventually, we were able to use it up to 20 megapascal, which corresponds to 2 kilometers in depth. We use these sensors for a couple of applications: underwater, on marine animals, also for monitoring as a wearable, in this case of the heart rate. And the printing process, of course, allows you to fabricate diverse arrays of sensors on a wearable structure and platform. Next, I move on to giant magnetoresistance sensors. Let's first define magnetoresistance. It is a change of electrical resistivity of a material if a magnetic field is applied. It is typically characterized by the MR ratio, the magnetoresistance ratio, which is a change in resistance over the resistance at zero magnetic field. Usually the MR ratio is given for the maximum delta R. The most common types of magnetoresistance are anisotropic magnetoresistance, giant and tunneling magnetoresistance, and I will focus on the later two here. The giant magnetoresistance sensors are composed of a multi-stack of alternating ferromagnetic and non-magnetic conducting layers. The basic principle can be explained with 3 layers: 2 ferromagnetic electrodes separated by a non-magnetic conducting layer. One of the 2 ferromagnetic electrodes is hard magnetic, the other one is soft magnetic. This is important because it means, as we apply an external magnetic field, the hard magnetic layer, in this case the left one, will not change its direction, whereas the soft magnetic layer, the right one, will change the direction depending on the direction of the external field. And in this case we see here a parallel alignment and an anti-parallel alignment of the ferromagnetic electrodes. Now, the best way to explain the giant magnetoresistance effect is by using mods to current model. Here we use a separate current density for the downspins and the upspins, and they are determined by a conductivity for the downspins and upspins, which are different from each other. Now, as an electron passes through a magnetic material, it gets spin polarized, and the thickness of the conducting separation layer has to be thin enough for the spin polarization to be maintained until the electrons reach the other ferromagnet. Now, mods to current model then adds the 2 current densities for the upspins and downspins to obtain the total current density. Now, the conductivities themselves are different because typically the minority spins, which in this case would be the downspins, have a higher number of density of states, and the density of states is indirectly proportional to the conductivity according to Drude's model, and therefore we have a high resistance for the minority electrons and a low resistance for the majority electrons. So if we draw a circuit model for such an arrangement, then the majority spins face a low resistance and basically no resistance in the conductor and another low resistance in the ferromagnet, whereas the minority electrons face a high resistance and another high resistance. In total, we have a low resistive path parallel to a high resistive path, which means we have a low resistance. In the anti-parallel alignment, we have majority spins here, which have a low resistance, but they become minority spins in this case, and therefore we find a high resistance. And the minority of this side have a high resistance, and they become a majority on the other side and have a low resistance. In total, we get two parallel paths, each having a low and a high resistance, and therefore the total resistance is high. Can be rather high and is very intriguing, and it was actually worth the Nobel Prize in Physics in 2007 for Albert Fert and Peter Grünberg, who developed this effect and discovered this effect, actually independently. Here we see again these two possible situations where we have a parallel alignment and an anti-parallel alignment, and the GMR ratio is simply the resistance at the anti-parallel case minus the parallel case divided by the parallel case. We see here a characteristic curve reported in 1988, and already back then 80% resistance change were achieved, which of course is very high. Now in between here we get a direction that is somewhere in between the parallel and anti-parallel direction, and this also means we can achieve a linear response. We can move the working point or operating point, for instance, to the center if we set the bias condition like this, where the free layer or soft magnetic layer is aligned 90 degrees to the magnetization of the pinned layer. And this configuration is not difficult to achieve with different methods, and is very popular for a linear effect with high sensitivity. I would like to show you an application of the giant magnetoresistance sensor in the field of biological detection. And what is commonly used in this area are superparamagnetic nanobeads, which can be functionalized by coating in order to target a specific analyte. This can be a bacteria, a virus, a DNA. Now, in this so-called bead trap detector for biodetection, we have a magnetic sensor, the GMR sensor, and on top of it we have a conductor. On top of that we have a trap or a well, and if we apply a current to the conductor, the magnetic field from this current will attract the beads, and the beads will fill the trap. And the number of beads that fit into the trap depends on the size of the beads and the size of the trap. If we have a sample, say a sample of blood, and we have our bacteria in the blood which we want to target, then each bead will be bigger in size because of the attached bacteria. Now, if we turn on the current, the beads will fall into the trap, but fewer beads will actually fill the trap. And the magnetic field that we sense from these beads with our magnetic sensor will be different in these two different cases. But actually, you don't even need the trap, not the mechanical trap at least, because the magnetic field sensor will have a region from which it can detect the magnetic field from the beads, which anyways is limited. So beads that are outside of this region will not be detected by the magnetic field sensor, and the principle still works. Let me show you the typical sizes that we're dealing with here. For instance, if we take an E. coli bacteria, it has a size of around 1 by 3 micrometers. In order to detect that, we used a superparamagnetic microbead with a diameter of 2.8 micrometer. This is a very common commercial microbead. The functional layer, which links those two together, is established through an antibody which is specific to the E. coli and a streptavidin biotin link. The size of that is around 50 nanometer and can be neglected. Therefore, if we look at such a bead bacteria constellation with the electron microscope, we see here the bead, and attached to it the E. coli. It's a bit difficult to see, therefore the outline is highlighted. Here maybe you can see the E. coli that is wrapped around the bead without the outline being highlighted. And this is a typical structure with which we detected these E. coli, but also other targets, an array of electrodes to trap the beads, not just into the well, but even to collect the beads from a larger area. In the middle, a trap, and here we see a trap filled with these beads. And here you see some results. For instance, if you want to detect nucleic acid, you see here that you get the highest sensor output because the most beads will fit in your trap if you have no target analyte. And as you increase the concentration of the nucleic acid, you get a decreasing output signal. And the same can be done with E. coli bacteria, where the increased concentration of the bacteria leads to a reduced. Then let us move on to the tunnel magnetoresistant sensors. TMR sensors are made of a multi-layer stack similar to GMR sensors, where we have now two ferromagnetic electrodes separated by an insulating layer. And this is the important difference compared to the conducting layers we used in GMR sensors. The effect was discovered in 1995, and one of the two magnetic layers is hard magnetic and the other one is soft magnetic. As in case of the GMR layers, this means an external magnetic field, which we would like to measure, will change the direction of the soft magnetic layer with respect to the direction of the hard magnetic layer. The spin polarized currents will tunnel through the insulation layer, and this will be a conductance dependent tunneling, whereby the conductance across the barrier is proportional to the product of the density of states on both sides. The effect is quite dramatic with TMR ratios up to 1000%, and the TMR ratio is defined in the same way as the GMR ratio, the resistance change over the original resistance, whereby the maximum resistance change occurs when we have the resistance of the anti-parallel state minus the resistance of the parallel state divided by the resistance of the parallel state gives the TMR ratio. And of course, this can also be expressed by the conductances or the current densities. As before, we have now two current densities that need to be considered, as given by Mott's current model, where we take into account the upspins and downspins current densities separately. Here we see a typical setup of a tunnel magnetoresistance sensor in a simplified model consisting of two ferromagnetic layers separated by an insulation layer. Here we have the parallel condition, and here we have the anti-parallel condition. In case of the parallel conditions, the electrons will find an easier way to tunnel through the barrier than in case of the anti-parallel condition. The conductivity in general is expressed as the sum of the product of the density of states of the two different spin directions. So let's take this parallel case. We have here the majority spins, which fill the energy band almost completely, as opposed to the minority spins. The density of states at the Fermi level is higher for the minority spins than for the majority spins, and as we have seen in case of the GMR sensor, this means the minority spins have a higher resistance. There is a separation between the left and the right Fermi levels of E times V due to the applied voltage. Now the majority spins will tunnel from a density of states condition with a low number to one with a low number, and the minority spins will tunnel from a high number to a high number. In terms of Mott's two current model, this means we have this condition where we have 2 times a low resistance in parallel to a series connection of high resistances. In total, we have a low resistance. In case of the anti-parallel alignment, the majority spins have a low number of density of states and tunnel into a high number of density of states, and the minority spins tunnel from a high number of density of states into a low number of density of states, meaning we have the situation in Mott's two current model where in both branches we have a high resistance, and therefore the total resistance will be high. In reality, the TMR sensor stack is quite complicated, as it consists of a large number of different layers, and on top of that the thickness of the layers is very small, which makes the fabrication rather challenging. We see here the free layer, the tunnel barrier with 2.05 nanometer, the pinned layer, a separation or spacer between the pinned layer and an antiferromagnet, and the antiferromagnet is actually what causes the pinned layer to be pinned. And as we see here, we can achieve different characteristic curves for such a tunnel junction, depending on the exact dimensions of these layers and also the composition. And for instance, we see here a layer with a rather high hysteresis, which is typically used for memory elements. And here we see a layer or a structure which has a very small hysteresis and a very linear response around zero magnetic field, which is of course a very good sensing element. In this case, we have a TMR ratio of 150%, and at zero field a sensitivity of almost 4% per Ørsted, which is actually very high. Now, how can we make a flexible tunnel magnetoresistant sensor? Well, this is not easy and was achieved for the first time in 2017. And the big challenge is actually this complicated material stack with these thin layers. It's impossible to fabricate a functioning magnetic tunnel junction on a rougher surface, and therefore the only material where it worked so far is a silicon wafer. Hence, if you want to get a flexible magnetoresistant sensor, the starting point is a silicon wafer, and you fabricate your TMR sensors on top of that, let's say in a standard fabrication process. Then you protect the surface of this wafer. You basically protect the magnetic tunnel junctions. In this case, we used photoresist. You flip the substrate around and then you start etching the backside until you reach a thickness that you have desired. Let's say 10 micrometer, 50 micrometer, 5 micrometer, and then you end up with a flexible tunnel, magnetic tunnel junction or tunnel magnetoresistance sensor. We characterize the flexible tunnel magnetoresistance sensors in different ways. First, we see here the change of the magnetic properties as a function of the bending diameter, and even down to a bending diameter of 500 micrometer, neither the saturation, magnetization, coercivity or remanence show a considerable change. We also tested the electrical properties as a function of the bending diameter, and as you can see, maximum and minimum resistance as well as TMR ratio are basically independent of bending. And this is also true for bending cycles up to 1000, which was the highest number we tested. We see here a cross-section image of the stack after the thinning, and as we can see, there seem to be no damages, and also the electron energy loss spectroscopy doesn't show any damages occurred to the stack. The noise behavior of the flexible tunnel junctions is the same as before flexing them, and also the magnetic properties do not change with up to 1000 cycles of bending. Now that we had a flexible tunnel magnetoresistant sensor, we were eager to put it to use. And the application we found was a catheter with magnetic orientation sensor. In particular, a cardiac catheter, which is used for many different conditions and which allows to use a minimal invasive surgery instead of an open heart surgery in order to repair heart valves, perform angiography, or also to place stents. Now, there are some disadvantages associated with this. The thing is that you want to see where your catheter is, and this can only be visualized with X-ray. So basically an X-ray video is taken as the catheter is inserted, and then in order to visualize the vessels, a contrast dye is pumped through the opening here at the tip of the catheter, which briefly visualizes the vessels. Now both the X-ray and the contrast dye of course have side effects, and this is what we wanted to avoid. And in order to do so, we were implementing a magnetic orientation sensor at the tip of the catheter. In particular, a 3-axis magnetic field sensor, sensitive enough to detect the orientation simply by the changes of the Earth magnetic field as you change the direction of the tip. Now, this sensor had to be highly miniaturized as to be able to fit at the tip of the catheter without really increasing the size, and also without changing the weight or the handling of the catheter. The substrate had to be flexible so that it can wrap around the catheter tip nicely. The tip had to maintain its opening, and it should have also a low power consumption. The result can be seen here. This is a typical cardiac catheter, and at its tip we have installed a flexible tunnel magnetoresistance sensor. There are different ways to implement the TMR sensor at the tip of the catheter. Here we see how a flexible TMR sensor is wrapped around the catheter and glued to it using a double-sided adhesive tape. Here you see the structures of the TMR sensors and the electrodes. The sensor after installation had a TMR ratio dependence over the angle as is seen here. We have the calculated and ideal response as the red curve and the blue one as the measured curve, and this was accomplished with a sensor that had a weight of only 8 microgram and it increased the diameter by 12 micrometers and the power consumption was as low as 30 nanowatts. Then I would like to move on to giant magnetoimpedance sensors. Giant magnetoimpedance sensors are characterized by an impedance change of a ferromagnetic conductor upon the change of a magnetic field. They produce very high sensitivities over small field ranges. As you can see here, a few 100% are typically achieved and were originally discovered in microwires. An example is shown here, which is a glass-coated iron silicon boron microwire. These wires, though they provide very high sensitivity and performance, are not easy to integrate in electronic circuits, and therefore thin-film giant magnetoimpedance sensors were also developed, and this is also what I focused on in my research. The structure that I preferred the most was a very simple 3-layer structure made of permalloy, copper and permalloy. And the thicknesses were very reasonable and easy to fabricate, 100 nanometer and 200 nanometers respectively. Now the principle of the giant magnetoimpedance sensor is actually rather simple. It can be realized even in a common iron slab, for instance. You send a current through your copper in case of the 3-layer structure, and you have a magnetization in the permalloy layers which is transverse to the current direction. This is caused by, for instance, induced anisotropy or by shape anisotropy. The current itself will generate a magnetic field which depends on the permeability. As you apply an external magnetic field along the direction of the current, the magnetization will be rotating out of its original axis along the direction of the magnetic field, and this in turn changes the permeability and hence the impedance of the sensor element. As you can see, this structure is actually very simple and therefore also robust, and it lends itself for the application in flexible sensors. The GMI sensor sensitivity depends on the frequency. Here you see a typical characterization curve of the sensitivity as a function of the frequency, and we get a maximum in this case of above 6% per Ørsted. The frequency range covers a couple of useful ISM frequency bands where you can apply the sensor wirelessly for different applications. And I'd like to show you an example here where I used a giant magnetoimpedance sensor for wireless operation in combination with a surface acoustic wave transponder. The surface acoustic wave transponder is a device that receives an RF signal, and via interdigitated electrodes it creates a surface acoustic wave which travels along the substrate. If it crosses or passes another interdigitated electrode, it will be reflected and also transmitted depending on the dimensions and geometry of these interdigitated electrodes. In case of this sensor, we connected the interdigitated electrodes, the reflector electrodes, to our giant magnetoimpedance sensor, which acts as a load for this IDT, and the reflection coming from this IDT is affected by the impedance of this GMI sensor, which in turn is affected by the magnetic field. And therefore we end up with a passive battery-free magnetic field sensor. The dimensions are shown here as an example compared to a coin. Here we see the time behavior of the reflection coefficient, and we have here the incoming IDT, and here the reflection IDT and the giant magnetoimpedance element, and we see that after around 3 microseconds we have the reflection from our load IDT. This is the signal that contains the information of the giant magnetoimpedance sensor. We also have other reflections. They typically come from the edges of the substrate. Now with this sensor we achieved a maximum amplitude change of 7.8 dB. But actually the more interesting thing, the sensitivity was 1.3 dB per Ørsted, the maximum resolution 3.5 milliOersted, the linear region was 3 Ørsted. Now, this can be useful, for instance, to detect a car. If you place such a sensor into the road bed underneath a car, then the signal that is created by a car as it disturbs the Earth's magnetic field is around 0.2 Ørsted, and our resolution is 3.5 milliOersted, so we can easily monitor whether there is a car or not. And remember, such sensors can be integrated in the road bed as it is fabricated or as it is made, and you do not need any wires or any batteries. We then expanded this concept by making a passive wireless and battery-free multifunctional sensor. It still included our GMI element, but now it also had a temperature sensor and a humidity sensor. The humidity sensor was realized by hydrogel coating on a delay line, which changed the velocity of the surface acoustic wave. The sensor was still very compact, as you can see here, and now we had 4 distinct reflection points. One was for the reference and the other 3 for the sensors. We tested the sensors individually for the humidity, the magnetic field and the temperature, and then all 3 of them at the same time. There was some cross sensitivity between the humidity and the temperature, as you can see here, and further calibration would be needed to avoid this effect. Now such a sensor has many applications. For instance, in power grid monitoring, where we can monitor the current, the humidity and the temperature at the same time, and we do not need any wiring or batteries there, which would need to be replaced. It can be used for construction monitoring to observe corrosion of reinforcements, structural reinforcements, and of course then it can also be used for corrosion monitoring of pipelines, again, where the magnetic signature changes over time as the material corrodes. Next, we wanted to develop flexible GMI sensors using the stack that we had developed before. Therefore, we deposited the 3-layer stack, 2 permanent layers sandwiching a copper layer on different substrates: photo paper, premium photo paper, and Kapton. It is remarkable how much the substrates affect the magnetic properties of the stack on top of it, as we can see here, and mainly this is related to the surface roughness. The regular photo paper shows the highest surface roughness and results in the highest coercivity, or the hardest magnetic material. The substrate with the smallest surface roughness, on the other hand, produces a relatively soft magnetic material. Now this is reasonable because surface roughness on the magnetic material will induce pinning sides for the magnetic domain motion, and the more pinning we get, the higher the coercivity. Obviously, this is reflected in the GMI sensor performance, and this is what we see here. The GMI ratio as a function of the external magnetic field is by far the highest in case of Kapton, which has the smallest surface roughness. We see here the giant magnetoimpedance ratio, the maximum value of it as a function of the frequency. It increases in this lower frequency range with the frequency, as we have seen before, and it's the highest for the smallest surface roughness substrate. And in turn, of course, this maximum sensitivity is also the highest in case of Kapton. In order to make use of these highly sensitive giant magnetoimpedance sensors, we developed an artificial skin. And for that, we borrowed a concept from nature, which is the cilium. The cilium is a micro hair that is found in many animals. Also humans use them, for instance, in the ear. And when a cilium gets bent, a neuron gets stimulated and a signal is transmitted. Our artificial cilium was made of micropillars, highly flexible micropillars made of a polymer filled with permanent magnetic particles, in this case magnetic nanowires. And the pillars were fabricated on top of a magnetic sensor, and at first we used the giant magnetoimpedance sensor. The stray field of the pillar was sensed by the sensor. And if a force causes bending of this pillar, the stray field would change and the magnetic sensor would read a different signal. Hence, we were sensitive to force. Now, the very nice thing about the cilium concept is that the sensitivity or measurement range can be tuned within a wide range simply by geometrical parameters. Especially the length and the diameter play a major role. So if you make the cilium thicker, for instance, it will be less sensitive, but you get a larger measurement range. And here in this video, you see how a micro hair array or a artificial cilia do different stimuli from outside. Eventually, we used not just GMI sensors, but also GMR and TMR sensors to realize these artificial skins. And overall, we achieved low power consumption, low weight, small size, and a high sensitivity. Now, this artificial skin responds very well to external pressure. If you apply force from the top, and here if this force is broken down to the pressure, then the impedance changes as is shown here. And the attractive feature of this magnetic sensor is that it's not affected by the permittivity of the surrounding material, and therefore it works in water and air in the same way. We realized these micropillars on a giant magnetoimpedance sensor that was fabricated on Kapton, and from this we actually got our artificial skin, which we were using then for different applications, like for instance heart rate monitoring. Putting it on the wrist, it was able to detect the changes of the surface due to the blood flow in the vessel. We used it also for braille reading. The letters that are used by blind people could be easily detected with an array of these micropillars. And then also here's an example where we used it for fluid flow sensing. Any flow bends the cilia, and we used it for air and water flow. And we achieved an extremely high resolution in case of water flow of 13 micrometers per second. And we had a power consumption of only 80 nanowatts. Here you see something else that I mentioned before. Changing the geometry of the cilia allows you to adjust the sensitivity or the range, and this is shown here. These cilia have the same length, but in one case they have 100 micrometer in diameter, and in the other case 250 micrometers. And they are exposed to water flow, and as we can see here, the impedance change is much faster in case of the thinner cilia, but it also saturates faster. The slope, of course, is the sensitivity, and the saturation tells us the range. So with the simple change of the diameter, we can create flow sensors, force sensors, pressure sensors for different applications. Next, I would like to move on to magnetic skins. Magnetic skins are the missing element for a truly flexible magnetic sensor system. We already have flexible magnetic field sensors, different versions of them based on different technologies. In combination with magnetic skins, we can get entire flexible systems. And these can be used for body tracking, sleep laboratories, driver vigilance, monitoring, remote control, and so on. We see here flexible skins mounted to a finger or to an animal. We see how stretchable it can be on a leaf, on the eyelid, or also on the hand. Now, how can we make these flexible skins or wearable magnets? Well, we use a matrix, combine it with magnetic powder that is hard magnetic, and we end up with composite permanent magnets. And they can be made into any shape and also any color, and therefore they can be catchy, like a tattoo, or they can be imperceptible. We use different materials for the polymer matrix, obviously PDMS, but also a lot we worked with EcoFlex, which is often used to mimic tissues, and it's very soft, and with that you can create extremely flexible sensors. And we can therefore produce flexible permanent magnets that are lightweight with tailor shape and magnetic properties, and they are the possibilities to tune the magnetic skin properties are shown here. First, we take a look at the mechanical properties. We have the stress over the strain, and the different curves here have different slopes, and the slope presents basically the Young's modulus. If we increase the content of magnetic powder, neodymium iron boron in this case, we increase the Young's modulus. And we can therefore change the stiffness, the elasticity, simply by changing the ratio between the elastomer and the magnetic powder. On the other hand, we can also tune the magnetic properties. As we see here, the more powder we put in our matrix, the higher the saturation magnetization and also the remanence magnetization. The coercive field, of course, is not affected. This is a property merely or depending on the powder that is being used. One of the applications where we use this magnetic skin in combination with magnetic sensors to realize a magnetic system was animal monitoring. And as you can see here, we developed different structures of magnetic skins in order to fit best the application. And we use them in combination with a TMR sensor device that used a Bluetooth transceiver to visualize the results on a cell phone. The TMR sensor was a 3-axis TMR sensor, and we applied this for the monitoring of different sea animals like turtles, giant clams, and also crabs. And we monitored the movement of the head or the legs or the opening and closing of the clam's shells. We also used it for eye movement tracking, and for this we implemented a magnetic skin on the lid of an eye, and we monitored the movement of this magnetic skin due to eye movement with magnetic field sensors that were integrated in smart glasses, which are not shown here. And this actually works really well. You would probably think this might be uncomfortable, but here we see the Young's modulus of a contact lens, a soft contact lens, versus a magnetic composite that we used here for the magnetic skin, and the contact lens is actually considerably harder and stiffer than our magnetic skin. And we attached the magnetic skin with Vaseline, or for instance, and therefore it was, after the Vaseline dried, it was not noticed by the users anymore. And then we monitor the magnetic field from this magnetic skin, and we can easily distinguish whether the eye is open or closed. We can therefore see the blink of the eye, but because the eyeball is not spherical but has a certain curvature, as the eye rotates, the magnetic skin comes further forward or backward, and therefore we can also see whether someone looks left or right. We see here that the signals that come from a magnetic field sensitivity in 2 different directions, and we can distinguish now looking up or down, looking left or right. And we implemented this to realize a smart wheelchair, where you can see here the user, that is a quadrileptic who cannot move the hands or legs or arms and can only move the eyes. And by the movement of the eyes, and there are the glasses, the smart glasses with which we monitor the magnetic skin, the user was able to control the wheelchair simply by moving the eyes or other facial gestures. And with this I came to the end, and I would like to thank you very much.